Assalamualaikum. Today I and my group members will present about modeling electromagnetic field in DC. Before I continue my presentation, let me introduce to you our group members. The first person is Faiz Afifi bin Hassan, which is me. The second person is Siti Nur Nambiha binti Nur Hassan. And the last person is Nik Nur Amsyah binti Nik Husni. Problem statement for this study is the development of modeling for calculation of electromagnetic field around the railway track using 3D finite element to reducing the model complexity from removal of longitudinal uniformity and increasing of conduction current within ground. Why use 3D finite track model? There is have three reasons. The first reason is 3D finite element more elegant solution compared to 2D finite element. The second reason is improve on simple analytical model used by railway engineer. The last reason is to enhance safety and gaining an understanding of condition of interaction between traction and track circuit current. And now I will present about the specification model. First is signaling track circuit termination area such as around block joint. Second is adding arrangement near power substation to determine ground current flow between grounding grid and rail connection. The last one is field distortion near critical point such as track cross bonding.
Okay, my name is Nino Ain Amsyah binti Husni. So next, I will present about the principle of finite element and the user procedure. So based on my research, with Maxwell's equation, we can solve the finite element, which is the Fe, by calculate the scalar or vector potential values at defined mesh nodes for the minimum energy condition through the minimization of a functional. So by interpolate with weight of shape functions over the space of each finite element, we will know the complete field distribution within the model. So this FE, which is finite element software, is designed for solution stability with minimization of the storage requirements and runtime, and also it is to define each material region in terms of its electrical conductivity, permeability and permittivity. So each region is then divided into triangular, quadrilateral elements which is for 2D, six-sided bricks, and triangular prisms for 3D, with size depending on the field changes. Okay, so next I will present about the rail track traction system. So for the 3D FE model, firstly we should consider the railway track geometry, which the track is a 3D structure that is laid on the surface of the ground, whose weakly conducting behavior affects the EM field distribution. So the fields from the currents will flow along the rails and the other parallel cables, which will spread into the air and ground. And then for the 2D modeling, the energy flow must be in the Z direction, which is shown in the figure in this slide. The track longitudinal symmetry requirement will implies that the fields must not change in the z direction. So this implies that the direction of conductive current that flow through the rail and ground at the slice in the figure must be normal to XY plane. That is the first. Second, change of the voltage due to series impedance, and third, change of rail current due to inter-rail admittance. Both must be small. And then lastly, the resultant electric field must be in the z direction also, which implies that the field arising from eddy currents must be much greater than that due to interrail and rail earth diffusion and it lost currents. Okay, lastly, I will present about the formulas that we use for this FE system. Okay, for the equations, the first equations for the eddy current part of the solution can be written in terms of the vector potential A, which is defined by magnetic flux density formula, which is B in this slide, where the AZ in the equation is the Z component of the vector potential. EA is the time integral of the applied electric field, and then the ITOT is the total current. Okay, for the second equation, the displacement and conductive current problem will solve by a different set of Maxwell's equations, which is E in the slide. So the equation to be solved is derived from Maxwell's equations as the last equation for Maxwell in this slide. So that's all from me. Thank you.
Okay, I will explain about 3D finite element of modeling traction system, which is about formulation problem. So first is from 2D to 3D model. We need to reduce computer resource because it is a large scale work. Second, we need to do the process of decoupling of two solutions because excitation along straight rails is only in Z direction. Some current flows to the earth, so it will traverse X and Y components in addition to Z. So the existing eddy current from the ground will less in magnitude than from concentration rail current. The required current excitation in the Z direction in rail and ground is an initial condition which must be determined from a separated period 3D division current model. Okay, next we move to the test, this is the practical traction return current test. As the figure shows the test condition, the current was fed from a substation to a locomotive along a straight level track over uniform ground. The current distribution in the feed, which is feed to catenary to contact wire, then to the parallel feeder, and return to rail or earth wire. It was measured at a test location at height 1168 meters from a substation, as the position and power demand of the locomotive were varied. The exact measurement conditions were implied with, in particular, the locomotive position in error by plus minus 5%. From the test, here is the result. The variation of propagation constant with current at table 1 could be due to change of ground condition during the test. So the interpretation using classic high-phase transmission line theory, assuming a uniform, which is single layer, ground conductivity yields and effective propagation. The effective propagation constant, which is decreased with increasing measurement section lengths. This implies that because for longer length the ground flows at greater depth, the effective rail to ground conductance and ground conductivity will reduce with the depth. So from the table, there are substation current, which is fader plus catenary plus contact wire for the rail current. It includes earth wire current. So from that we can see the largest and the smallest effective rail to ground conductance range from 2.93 meter ms per m to 12.6 ms per m, assuming an effective rail return resistance of 15 milliQ per m. Okay, next is a 3D traction system modeling. So for figure 3A, which is rail are represented as an equivalent semi-cylinder that set into the ground. It is divided into layered semi-segment. So in this way, the model depart from reality, which are: first, the rail ground contact is a continuous cylindrical surface in uniform contact with the inner soil layer, instead of through the rail fastener, ties and ballast. Second, the ground conductivity stratification are cylindrical in the model rather than horizontal in practice. Third is the boundary condition in the model are that non-horizontal current enters or leave the line at the points of current injection. So for the figure 3B, we can see the model geometry enables analytical calculation of the equivalent series resistance and shunt conductance values of each ground layer, which is either necessary for the formation of equivalent multi-conductor transmission line, which is MTL. It verified by circuit simulation using a grid of equivalent resistance and conductance from figure 3B. So for figure 3C, which is that figure from MATLAB result, we use MATLAB software for solve the MTL for the given excitation and boundary conditions by a model calculation routines. The model was set up with the dimension and conductivities of the cable and ground layers chosen to produce the same order of magnitude for the thread currents and voltage. A 3-layer ground conductivity profile was then imposed on the model to improve the result. Okay, based on this table, it was an improvement compared with constant ground conductivity model implicit in propagation constant of first result. Okay, finally is the finite element model, which is we need to add some other consideration after do some calculation. First thing first is model size, which is as shown as the figure. This is the mesh model of finite element of 3D DC traction model. Next consideration is the element size. Other than that, a boundary condition, boundary distance, and solution convergence that need to be taken in the process to create the 3D model of the traction system. That's all from us. Thank you for watching.